Welcome to This Explainer. Today, we're tackling what is, without a doubt, one of the absolute most pressing engineering bottlenecks of our time, and that's keeping artificial intelligence from literally melting itself down. We're going to take a super fascinating journey today. We'll start by looking at massive industrial-scale data center plumbing, and then we're going to zoom all the way down to microscopic fluid channels etched directly into the back of silicon chips. It's an incredible story of physics, bio-inspired engineering, and macro-scale infrastructure. Now, to understand why the entire AI industry is going through this massive structural shift right now, you really only need to know this one simple physics fact. Water transfers heat 3,500 times better than air. Right? For decades, just blowing cold air over hot computer parts worked perfectly fine. But with the latest generation of AI hardware, air cooling hasn't just become inefficient, it has fundamentally hit its physical limit. Okay, let's dive into this. To give you a real sense of the scale we're talking about here, a single GB200 NVL72 AI server generates a staggering 10,000 watts of heat. Just one. That is an unprecedented thermal challenge. We are no longer dealing with hardware that just gets, a little warm. We're dealing with silicon processors that generate enormous, concentrated internal heat that traditional cooling systems literally cannot keep up with. So here's our roadmap for today. We'll cover the AI thermal wall, direct-to-chip liquid cooling, generative microfluidic channel design, distributing the liquid coolant, and finally wrap up with the sustainable AI factory. All right, Section 1, the AI thermal wall, pushing air to the limit. If you've ever stood inside a traditional data center, you know it's completely defined by the deafening noise of massive fans pushing chilled air. But when server racks start hitting 50 to 100 kilowatts of power density, the physics of air cooling just become totally unforgiving. To cool 100 kilowatts with air, you need to push about 15,700 cubic feet of air per minute. That's literally the equivalent of trying to force a hurricane through a 2-inch gap in a server intake. And yeah, it is exactly as loud and chaotic as it sounds. But here's the real killer. While your airflow needs increase linearly, the power required to run those fans scales cubically. It creates this vicious energy consumption spiral that rapidly gets out of control. It just becomes economically and practically impossible. Moving on to Section 2, direct-to-chip liquid cooling, going to the source. So, if air no longer works, we have to bring the cooling medium directly to the source. As we know, overheated chips will automatically trigger thermal throttling, and that can slash your computing performance by a massive 50%. Now, standard liquid cold plates definitely help, but they basically sit on top of the chips alongside all these protective layers that actually act like a thermal blanket. So by removing those blanket layers and routing the liquid directly into the silicon itself, we can cool these chips up to 3 times better. It's a total game changer. Section 3, generative microfluidic channel design. AI, designing for AI. Now, what's really interesting is that this is exactly where the micro magic happens. If you look at the heat map on the left, you'll see these intense thermal hotspots on an AI superchip. Now, traditional microchannels are just, straight parallel lines. But by using generative design, algorithms can actually create these incredible bio-inspired microchannel patterns. These organic shapes optimize the dynamic fluid dynamics inside the chip, minimizing pressure drops and routing the exact right volume of coolant exactly where those thermal hotspots demand it. To actually achieve this, researchers at Microsoft and a startup called Corinthus used a reaction diffusion process. Specifically, they used the Gray-Scott model. Now, this is the exact same mathematical system that dictates how nature forms the veins in a leaf, or the complex patterns on a butterfly wing. Nature has already proven brilliant at finding the most efficient routes to distribute fluids, right? So the engineering challenge was just dialing it in perfectly, optimizing the fluid velocities so the channels don't clog up, while making absolutely sure the delicate silicon doesn't break under pressure. And the data proves just how effective this breakthrough really is. When researchers tested these generative organic channels against standard straight parallel ones, the results were honestly staggering. Just look at the maximum peak temperature. The straight channels hit over 72 degrees Celsius, but the generative channels, they dropped that down to just 36.32 degrees. That is a massive 35-degree drop in maximum temperature. It completely eliminates those thermal bottlenecks we were just talking about. So what does this actually mean in the real world? Well, it's all about dynamic workloads. Think about an enterprise application like Microsoft Teams. Most calls start right on the hour or the half hour, which creates a massive, sudden spike in compute demand. With microfluidic cooling directly managing the silicon's temperature, data centers can safely overclock the processors. They can run them much harder and faster during these peak times without any fear of melting the chips.
Let's move to Section 4, Distributing the Liquid Coolant, the macro view.
So zooming back out from the microscopic world of silicon etching, you always need a massive secondary fluid network to make this all work at scale. It starts with a coolant distribution unit, or CDU, which basically acts as the heart of the system, managing pressure and temperature. Next, you have these massive row-based manifolds made of 304L stainless steel that act as the arteries, distributing the liquid safely across the server rows. And finally, quick disconnects deliver the fluid precisely into the individual in-rack servers. Notice how these heavy-duty row-based manifolds bridge the gap between the CDU and the really dense server racks. Because we're pumping pressurized liquid over incredibly expensive electronics, these manifolds are completely prefabricated and pressure-tested long before they ever arrive on site. Plus, the entire system is embedded with IoT leak detection sensors, keeping this entire high-density liquid infrastructure incredibly safe and stable. Finally, Section 5, the Sustainable AI Factory. A hotter, greener future. Now, you might assume that running all this massive liquid plumbing requires immense amounts of water and power, but the reality is actually a surprising environmental win. First off, it's important to note that while liquid is doing the heavy lifting, removing 70 to 75% of the heat directly from those massive GPUs and CPUs, most modern systems are still hybrid. We do still rely on a small amount of perimeter air cooling, maybe 25 to 30%, just to handle the residual components like memory drives and power supplies. But here is the most paradigm-shifting fact about this new technology. The liquid doesn't actually need to be freezing cold. Because the liquid touches the hot silicon directly, the coolant entering the servers can be as warm as 45 degrees Celsius. That's 113 degrees Fahrenheit. That is literally hotter than a hot tub. This completely shatters the decades-old myth that a data center has to feel like a walk-in freezer just to be efficient. And because the servers can happily accept this warmer coolant, facilities can skip those power-hungry mechanical chillers entirely and simply use large outdoor dry coolers to reject the heat directly into the ambient air. For most climates, this means you can run the facility almost the entire year, utilizing warm summer air to adequately cool the water loop. It is incredibly efficient. So the crucial takeaway here is this. We are looking at an ultimate sustainability win. These are closed-loop systems. Once they're filled, they don't consume any new water, which eliminates the millions of gallons of evaporative water loss associated with traditional cooling towers. Plus, without those hurricane-force fans blowing everywhere, these high-density AI factories will be eerily quiet compared to the deafening data centers of the past. Which leaves us with this final crazy thought. If we can use generative AI to design bio-inspired microfluidic channels, and engineers are already figuring out how to dynamically flow liquid vertically between stacked 3D chips, literally like concrete pillars in a multi-level parking garage, what are the true physical limits of the AI revolution? We've somehow found a way to literally keep the future of AI from burning itself out. Thank you so much for joining me for this explainer. I really hope you found this deep dive as fascinating as I did.